Recording in progress.
Okay, last week, I started on this self-oscillating adaptive system. So today we finish it. Now the key thing is that we still use the relay, and the relay is still on-off switch. When the input is positive, it is plus D. When the input is negative, it is minus D. All right, this is the input, except that now you see the input is a sine wave plus a DC or low frequency. All right, and so the relay will be not a pure square wave, but you will have some rectangular shape which contains a DC value in the rectangular wave also. Now, it's standard in engineering when you have AC and DC mix, we will separate the analysis into two parts, the DC analysis and the AC analysis. AC, I use the word AC to mean the sine wave, alternating current. In electrical engineering, we call basically AC, alternating current, and it's a sine wave. So you will have the relay can be seen as have a gain to the DC input. So you have a DC input, that's the B. All right, here the B here, the DC input, which is this one, and then the sine wave, which is the A sine omega t here, and the relay will have a AC gain, which means the DC pass through the relay multiplied by the DC gain, the AC pass through the relay multiplied by the AC gain. Okay, so now the maths gives the following key results. The main thing to understand would be this. The key result is that the AC gain is equals to 2 times the DC gain. All right, so that's the first key result. Then, as a consequence of this key result, what would then be obtained is that the gain margin of such a system, all right, will always be, the math shows, it's algebra, you just substitute here, substitute there, then you find that, how come the magnitude of the low frequency transfer function at omega u, the crossover frequency, is equal to 0.5. And this is defined as gain margin. So the key result is that if you have 0.5, then the gain margin is equals to 2. So this should be 1 over gain margin is equals to this. So gain margin or amplitude margin is the same thing. Gain margin or amplitude margin is the same thing, is equals to 2. That is the key result. Because of the maths that says that the AC gain is always 2 times the DC gain, and as a result, inverse, because the AC gain always give the 1. All right, always give 1. I think there should be a U here at a crossover frequency. And we see before, in order for you to oscillate like that, here must always be equals to, the amplitude must be equals to 1 or minus 1. And since the DC gain must be half of the AC gain, so that's why, as far as the low frequency is concerned, at the crossover frequency omega u, it appears to have a gain of half. And then that's defined as the gain margin. If you remember classical control, you will draw the Nyquist plot like that. And then this would be omega u. This would be omega u. As far as AC gain is concerned, the omega u is at -1. As far as DC gain is concerned, or the low, should say accurately, the low frequency signal or the DC signal is concerned, the crossover frequency is at -0.5. Okay, so now the only things can be clear only if we see the picture. Now, so the example was this. This is the MATLAB simulation when you have the relay amplitude is fixed at 0.35. Now, because it's a relay, the whole thing will oscillate. And we calculated that the oscillation will be at 0.05. How does it oscillate? What is the frequency? That is standard calculation. Let me go back. We basically make use of the fact that from here to here is equals to -1. All right, from here to here is equals to -1. So all you need to do is we look at this previous question. From there, we found that the oscillation frequency is root alpha. All right, this result was obtained from the basic example in previously. You could look back. So that is old stuff. There's nothing new here. Use the old stuff. All right, because the gain here is from here to here. From here to here is always -1, old stuff. You use the old equation, you will calculate and get alpha, square root alpha. So once you have square root alpha, then you look at here at square root alpha, what is the gain here? So you find what is the magnitude here. So since G is given like that, all right, this was obtained in the previous tutorial also. So the magnitude, since alpha in the question is given as 20, K is 3, so you will have 3/21. Then you will have the input, which is 0.35 times 3/21. Yeah, so 0.35 times 3/21 will give you the amplitude of the oscillation frequency. And that one is 0.005. I think I did it here. All right, 0.05. So we have, this is equals to 1/7. So 1/7, how we get E naught? E naught must be equals to D is 0.35 times 1/7. All right. So that will give us this. So now this part is done. And the next thing is that we see that, oh, what is the AC gain? So you look at the AC, this is 0.05. We simplify and think of this rectangular wave, the magnitude is the magnitude of the sine wave that can approximate this rectangle wave. So we think that this is a sine wave of amplitude 0.35. So what is the gain? So it's 0.35 over 0.05 will be 7. So as far as this part is concerned, the AC gain is 7. If the AC gain is 7, then the DC gain should be half, because that was the result. So the AC gain should be 7 over, no, so the DC gain should be 7 over 2. Okay, and the key result, the math shows that with a gain of 7 over 2, your gain margin will be 2. Because the control system has a nice gain margin of 2, that's why if you see you do a step input, the step response is quite nice. All right. If the gain margin is maybe 10, or then you will see it will be very sluggish, very, very slow. Or if the gain margin is very, very small, maybe 1.1, then you will find that the oscillation is very oscillatory. All right. You may forget your classical control, but this is classical control. People know that gain margin that is very close to 1. When gain margin of 1, you basically have oscillation like that. All right, you will have oscillation, sustained oscillation. So a gain margin of close to 1, let's say 1.5, you will have oscillation, though the oscillation will die, but you will have oscillation. So gain margin of 2 will look a little bit bad. So now, where is the adaptation? So the MATLAB simulation then shows that at t equals to 25 seconds, the plant gain increased by, I think, 5 times. So if we increase by 5 times, you will see that previously the is 0.05, now it becomes 0.25, because if the input sine wave is the same or the rectangle wave the same, since the gain of the plant is increased by 5 times, the output should increase by 5 times from here to here. All right. And so now, if the output, you see, this is, if you look at the picture looks like that. If previously this was 0.05, then this is 0.35. If the gain of this increased by 5 times, then of course from 0.05, the sine wave will jump to 0.25. This is what it means. But even though it jumps, the gain of this increased by 5 times. So what is the AC gain? So you take this 0.35 divided by 0.25 is 7 over 5. But the DC gain or the low frequency gain is always half. So you take this divided by 2. And then if you look at the DC gain, the low frequency gain of the relay, this is 5 times smaller than this. So means what? NB is the low frequency gain of the relay. It's 5 times smaller than before. So if you look at the picture now, this increased by 5 times, this decreased by 5 times. Okay, so the basically you will think that the crossover frequency, the gain margin will not change. That's it. Because you know how to draw the Nyquist curve, is this times this. When you draw the Nyquist curve, in general, let me see where's the Nyquist. Sure. You have this. In general, when you draw this curve, how we draw? We always draw the Nyquist curve as in a standard closed loop control system, whereby you have a controller and then a plant, and then a plant, all right. This curve here is drawn as GP J omega GC J omega. Then you let omega equals to 0, 1, 2, 3, 4, 5, 6, 7, 8, 10, you will get this curve. So if this is increased by 5, this is decreased by 5, you get the same curve. So which means you get the same curve here. And so because you get the same Nyquist curve, you look at this low frequency response, this part and this part, the step response shows you that it looks the same. All right, this looks the same. So that is the key idea. Now, after going through the key idea, the problem with this implementation is that you can't use it because your output is oscillating like that. So that is bad, you know. So in practice, you want to get this oscillation to something that is small and acceptable. So we want to get to something that looks like that. Then you see this one. All right. So the specification for this is the same plant, same system, but nothing has changed. But the only thing has changed is that you specify the following. First of all, the relay did not change, so you have the same old relay. If it's the same old relay, then here, like the previous example, D is equals to 0.35. No change to the relay. Then the next thing is the new specification. You cannot stand having such oscillation of 0.05 here. So you reduce it to 0.01. So which means now you want this to be at 0.01. All right. So how to do that? The trick is now you put in a lead compensator. So before you do that, you find out, okay, if the input is 0.35, the output is 1. So the gain of the plant, you look back at the picture here. If input is 0.35, the output is 0.01. So what is the gain here? So the gain here must be equals to 0.01 divided by 0.35. Okay, that must be the gain here. But the plant is the plant. You cannot change the plant. I mean, if I give you a heater, that's the same old heater. So what are you going to do? So you operate at a higher frequency, so that at a higher frequency, the gain of this become 0.01 divided by 0.35. Because at different frequency, you see the Nyquist curve shows that this is a Nyquist curve. At different frequency, you have different gain. So you choose the frequency that give you a gain of 0.01 divided by 0.35. So let's go and find that frequency. So you look at the maths. All right. This is the gain that you're supposed to have. Omega U prime is the new frequency. And since G is like that, it's given like that. All right, you multiply things out. You find the amplitude is like that. Then you take this amplitude, you equate it to this. All right, and you solve for, sorry, this should be omega prime, prime, and prime. All right, then you solve for omega prime, it will give you 10. So at a higher frequency of omega u prime 10, your gain now of the plant is smaller, is 0.028. Previously, you will compare to the previous example, the gain of the plant was 3/21. So it's 1/7. It's bigger. All right. Now, previous was 3/21. Now, it is 0.02. So it's obviously much smaller than 3/21. Okay. So how to make the plant operate at this frequency of oscillation? The trick is now stick in a lead compensator. Means what? Means that, let me draw here. All right, stick in a lead compensator here. Here. So means what? Let me draw a new picture. Okay. As before, stick in a new compensator, GF. Then you go to your relay. No change, 0.35. Then you go to your plant, no change. All right. As usual, we write this as 0 to make life easy. So that right now, the gain from here to here is -1. And then what you want would be the oscillation here we calculated was omega u prime is 10. And we want the amplitude here to be 0.01. Okay, so lead compensator, we write down the transfer function. It is given like that. I cannot teach lead compensator anymore, but we'll just go through it. Where is the lead compensator? Okay, the lead compensator. Yeah, right. The lead compensator will look is given by this. Okay, which means the lead compensator has this K into S plus T1 and S plus T2. So our last problem is find KF T1 T2. So to stick it inside here, right? Let me. So now we form this equation from here to here. The phase must be equal to, because from here to here is -1. So the phase from here to here, -1, I mean, if we write in complex number, is equals to magnitude 1, phase minus pi. Okay, so the first thing you do is find the phase of this. The phase of this, you must know how to find the phase of this. It's like that. All right, the phase of this is like that. Argument means phase of this, and it is given by this is arctangent of j omega. The phase of a complex number j omega plus t1 is just arctangent of j omega, or arctangent of omega over t1. Then this is j, all this has to be replaced by j omega. So the phase of this, now this one is your GF. All right. Geez, I wrote down here. So you need to find the phase of GF. The phase of K is 0, so you don't include it. Or you want, you put a 0 here. That's the phase of K. The phase of the numerator is just omega u prime over T1. The phase of the denominator is omega u prime over T2 arctangent. And because in the denominator, you do a minus here. So these are secondary school complex numbers, so I can't teach anymore. The phase of this, if you remember the plant transfer function, the plant transfer function is K alpha over S into S plus 1, S plus alpha. Okay. So you replace this by J omega, J omega, J omega. So this would be the phase of this. 1 over j omega, the phase is minus pi over 2. The phase of this, just like before, is omega u prime over 1. Just like this, because t1 is 1, so it's omega u prime over 1. You write over 1, it doesn't matter. Then the phase of this is omega u prime over alpha, so it's this. Then the whole thing must be equal to minus pi. So I showed you before, this whole thing must be equal to minus pi when you consider the phase of all this. So once you, for as far as lead compensator design, I can't teach anymore. This, from here onwards, the designer will have to choose T1 and T2. All right, because you have only one equation, two unknown. So normally which means there's an infinite number of T1, T2. So normally we will try to choose T1 and T2 as close to each other as possible, such that it will satisfy this equation. All right, that is classical control. You will learn when first do control engineering. So I can't teach you anymore, but you will try to, as far as I'm concerned, just choose any T1, T2 that satisfy this equation and try to make T1 and T2 as close to one another as possible. That's it. All right, this is a design problem. Then after once you, so you got T1, T2, we choose it at 15 and 5. So if we, this whole thing will be equals to minus pi. Of course, omega u already solved is 10. So you stick it there. Then after that, you still have a problem of choosing KF. KF choose such that the amplitude of this is approximately equals to 1. So this is 10, this is 10, this is 5, this is 15. Go and find the amplitude of this equate to 1, then you from there you solve for KF. Okay. So once you have that, then you will find that what will happen now, you have solved for this, you oscillate at the new omega u. Okay. Then you can say as before, what is the AC gain? The AC gain is NA equals to, you look at, this is 3.5, this is 0.01. So it's equals to 0.35 over 0.01. So it's equals to 35. So what is the DC gain? It's always half. Then somewhere here, the plant gain increased by 5 times. So if the plant gain increased by 5 times, the oscillation will now increase to 5 times 0.05. And since the relay have not changed, what is the AC gain? The AC gain 0.35 that is 7. And the DC gain will be always half, 7 over 2. Just like the plant change from here times 5 to here. Maybe I write properly. Then you see, here the plant times 5. Here you divide by 5. Okay? So NV will compensate for this. So you get the same old gain margin of 2. So this one and this one, the step response is a gain margin of 2 type of step response. Okay, go for a break. Come back at 7:05. Then we go through one tutorial question. Okay, so the question give the following. GC is 1 now, so this is 1. So this is 1. Then GP is 1 over S, e to the power of minus S. So it's 1 over S, e to the power of minus S. And relay amplitude is plus or minus 0.1. So it is like that. So this is 0.1. All right. So then question A, what is the amplitude and frequency of the oscillation in Y? All right. So amplitude and frequency of the oscillation in Y, because there's a relay here, 1 is, there's nothing there. So from here to here must be equals to -1. Right? So if that's the case, from here to here, the phase is 0. All right? Because if this is positive, this is also positive, this is negative, this is also negative. So the phase is 0. You know what is phase shift? When you have two sine wave, then it looks something like that. There's a phase shift. All right. But from here to here, it's like that. All right. So phi is equals to 0. If you just think of the relay as a sine wave, then you got two sine waves that exactly no shift. Okay. So if from here to here is 0, from here to here is also 0. It's 1. If you have a sine wave here, you have the same sine wave here. So it's also 0. So 0. So which means this is equals to 1 minus pi. The phase of this must be equals to minus pi. So the phase of this, just look at the answer, is written as, in case you are not familiar, then I just work out the maths for you. 1 over S e to the power of minus S. You will replace it by 1 over j omega e to the power of minus j omega. The phase of this part is forever minus pi. The phase of this part is forever just the power only. So is this one. Okay. So here is minus j omega, so it's minus omega. If it's minus 7, so it's minus 7. Sorry, minus j7, then it's minus 7. Whatever the number, right? Okay, so this must be equals to minus pi. Like I explained why I equate it to minus pi, because the phase of this must be equal to minus pi. The phase of this 0, phase of this 0. So all add up together, you just have the phase of this. So equate to minus pi, you solve for this, you will get the frequency of the oscillation. So that is the first answer. Then the second answer, what is the amplitude of the oscillation? So you need to find the magnitude of this. So it's 1 over j, what is omega? Pi over 2. E to the power of minus j pi over 2. All right. So you find this. Now, D is this one is 0.1. So 0.1 times this must be equals to, I want the oscillation amplitude to be what? The question say what? 0.04. So 0.04. No, I'm solving the wrong question. Okay, what is the amplitude? Okay, I'm solving the wrong question. So this, with this, it must be equals to what? So the phase of this is the amplitude of this is always 1. So it's just equals to 0.1 times the amplitude of this is just 1 over pi over 2. So everything you will get 0.2 over pi. So that would be the amplitude of y. So you're expecting a frequency here of this. Okay. With the frequency of okay, so it's question A. Question B. Question B. Asks you to design a self-oscillating system to give a gain margin of 2. Gain margin of 2, you forever will get a gain margin of 2. So you don't have to bother about that. Such that you have an amplitude of 0.04 in Y. So now, what you need now in question 2 is this amplitude here is going to be 0.04. So here is still 0.1. If you don't do anything, the amplitude here will pi over 4. Pi is about 3, so it's 1.5. But you want to reduce it to 0.04. So input 0.1, output 0.04. The gain of this must be much less. It must be 0.04 divided by 0.1. So how to get that gain? Choose a omega that is much bigger than pi over 2. So let's form the equation. So the new gain, input is 0.1. I'm now going to find a new gain, so a new omega that is equals to 0.04. All right. So this thing will give you this. Equate it to 0.04. You find omega is 2.5. So with omega 2.5, now you must have a omega u 2.5. With omega u 2.5, the gain of this will be 0.04 over 0.1. How do you make sure that you have this omega u of 0.04? Put in your lead compensator KF S plus T1, S plus T2. So that from here to here, you still will get -1 with omega u at 0.25. So the phase of this, you have to write down the phase of this. The phase of this arctangent of, again, is nothing. Arctangent of this, you got arctangent of this must be omega u over T1 minus arctangent omega u over T2. All right, that would be the phase of this. Then add on to the phase of this. The phase of this is 0. So you add on also, you add 0. So this plus the phase of this. The phase of this we see before is minus pi over 2 minus omega. All right, that's the phase of this. So you add all this together, you will get this equation here. And it must be equal to minus pi. So I connect for you properly. So this one must go up where it comes from. All right. This plus this. And then it must be equal to minus pi. So you got this equation. As usual, you got one equation, two unknown, so you just choose. So I just choose 1 and 10. So if you choose 1 and 10 is satisfied, then that's okay. Don't forget omega is what? 2.5, is it? Yeah. I think it's 2.5. Yep, 2.5. This is this one. And then choose such that the gain of the GF which is written like that is equals to 1. So you just find for it, K is 3.8. All right. Then after that, 3C. 3C says the plan has changed. So the plan has changed is 3 over S minus half. So the plan has changed. So now the plan is this one. So what is the amplitude and frequency of the oscillation? It's still the same equation. You take the phase of this plus this equals to minus pi. So this is the phase of this. This is the phase of GF. This is the phase of GP equated to minus pi. So you do the maths, you find the frequency is 5. Same, this is the relay. This is the GP. Then you do the maths, you get 0.06. Then last question, what is the gain margin? The gain margin is forever 2. So what is the gain margin? Gain margin is 2. This is forever 2. This is an adaptive system. No matter how your plant change from here to here or here to here, you will get a gain margin of 2, so that your control system performance is at a gain margin of 2. Okay, so I finished this topic. By the way, this was a previous year exam question. So, if you want to know how does exam question look like, it looks like that. All right, I teach you everything already. Now let's go to next topic. It's an easy topic. Gain scheduling. Now I told you about gain scheduling before without telling you, the story was here. I tell the story here about gain scheduling. Gain scheduling is here. So now we are talking about this one. This one, you remember when I draw the picture, it is this type, whereby your plant transfer function will change. So your controller must change because the plant change. If you're at this level, the plant change. So the controller must change. But the point is, because plant is forever like that or like that, at different level, you can calculate the transfer function. So become predictable. So all you need to know, if you are controlling the level, at this level, you will have a certain plant which you can calculate. Then from there you back calculate the controller. Then at here you have a new plant which you can calculate. Then you back calculate the controller. So the controller will compensate for the differences in the plant. All right, and the plant change according to the level, so it's predictable. If it's this level today, this transfer function, next year, this same level will be at the same transfer function, no change. The change is if we change level, then change. All right, so gain scheduling. And the maths is easy because it uses secondary school maths. Taylor series. Okay, we revise our Taylor series. Now, Taylor series, when we first learn, is always like that. In secondary school, I think we learn this type of thing. Secondary school is always X and Y. So you got X, you got Y. Then between X and Y, you have a curve. All right. Then they will tell you, when X is at X bar, Y would be at Y bar. Then they'll tell you, what is the value of Y when X changed to a new position? The answer should be this new value of Y. But we always then go and find the gradient here. And use the gradient to calculate the new Y. And this new y is actually an approximation. So how does the maths look like? This we always do this. This is y is approximate y minus y bar. This is x minus x bar. So we have dy dx at x bar, which means the gradient here is equals to this one, the approximate y minus y bar divided by x minus x bar. All right. Then if you rewrite everything, you have the approximate y is equals to y bar plus dy dx at x bar multiplied by x minus x bar. Hey, have you seen this equation before? Hello? This is Taylor series. Plus many, when you first study differentiation, one of the application they will make you do this. All right, and then we will then say this is approximate y. So we'll just in engineering we'll say the approximation is good enough, then we'll just take this as y. All right, so this is nothing new. This is secondary school stuff. Any problem? You all should see before. Okay. This is gradient, horizontal divided by vertical. It's dy dx. All right. Okay. So now we study a specific example to get the idea. If not, we talk in vacuum is very hard. So now we want to control the level in these two spherical tanks, the level of x2 length at the second tank. So we have two tanks. This is quite common in chemical engineering. You have chemical going into tank 1, then they mix, then chemical reaction takes place. Then after that, you will flow to tank 2, then mix. Chemical reaction takes place, then go out, then go to another stage. So now the control problem is to control the level in x2. First of all, we need to write down, take the maths book, and then you can see that the maths says that the volume of this is a sphere. The volume of the chemical here is given by this formula. All right, so we just accept it is from maths book. I mean, it's the how to calculate volume. If your height is x and then your radius is r, then you use this, you get the volume. So which means the radius is r, the height is x. You use that formula, you get the volume here. Okay? Then you differentiate dV dt. So if you differentiate, then you take this one, put 2, differentiate x squared, you get 2x times x dot. So you get this. Okay, then now think of 1 second because it's a rate. So in 1 second, the amount of chemical that flow in here minus the amount of chemical that flow out here must be equals to the change in the volume here. The volume here. So U is the amount of chemical that flows in 1 second. So you take U minus the amount of chemical that flows out in 1 second. This one, again, is a math equation. It's nothing to do with control. It's a proportion to the square root of the height difference. So x naught is this, x is this. So the square root of the height difference multiplied by a proportional gain would be equals to the amount that flow out in 1 second. Then that must be equals to the change in the volume in 1 second. So change in volume in 1 second is basically dV dt, is speed. Right? dV dt is speed. This speed is meters per second, cubic meters per second is called speed. Speed are things that changes in 1 second. So what goes in 1 second, what drops out in 1 second equals to this one. The change in 1 second. The change in volume in 1 second. So that's for the first tank. Then this one, what goes out from the first tank in 1 second is this one, minus what goes out in the second tank in 1 second. What goes out here? Same formula as this, but here you take the x2 as the height. Must be equals to, this is an equal sign. Equals to the change, the speed, the change in the volume in 1 second. So it is fixed from this one. So x become x2. Okay, so we got the equation. Then just rearrange into, I call the state space form. State space form is always the x1, x2, and then the dots is always on the left. So you go and right, you right. So x1 dot, x2 dot. On the right, got no dots. So you just on the right, no dots. The first equation I call it G. The second equation I call it H. Okay, then after that, I do this. All right, see how I do this? Nu equals to O plus the gradient times the change. Except that when we were in secondary school, you only have x and y, 2 variables. Now you have a lot more variable. So it's the same idea. The nu, which means the new one here, the new G is equals to the OG plus dg dx1 times x1, dg dx2 times x2, dg du times delta u. If you look at this, you will see it's the same. This is dy dx at x bar times delta x, right, equals to, if you like, I put O nu. Okay, so this is nu, this is O. All right, the OG, this is the OG. How come it's OG? Because the bar are all the O1. If you look at this, This is the old value. All right. Y bar is the old one. When you have the bars are the old one. This is the old one. All right. This. So these are at the bar, the old one. dg dx1 times delta x1. Basically now, because you got x1, x2, and u. Last time you only got delta x, secondary school delta x. Okay, it's the same idea, nothing has changed. So you use this and then this to write these two equations. The G equation and the H equation to find the new G and the new H. Then after that, if you see this, you just do some reorganization. Bring this over here. That's not good. All right, bring this over here. You will have delta x1 dot. So delta x1 dot. I think I should put the dot here. And then I put a dot here. So nu minus O will be delta x1 dot. Then this will be x1, x2 times dg dx1, dg dx2. You see, this is delta x1, delta x2, dg dx1, dg dx2. So this will be this one. Then this will be this one times this one. Then add this one times dg du. This one is dh du. So this one. So which means this now is reorganized into this. All right, it's obvious this is reorganized into this. And then this is reorganized into this. Okay. It's just algebra to rewrite this equation. Then and then after that, now this one is standard state space. With this, so I call this A. I call this B. I call this C. So this is a standard state space. It's a linear system. It's a linear system now. All right. And you can convert this to transfer function. The formula is like that. So I can't teach the conversion of state space ABC, or some people like to call it FGH, doesn't matter, to this transfer function. And all the dg dx, dg du, dg dx2, all this you have to do the differentiation here. So you I do for you here. So dg du is this, dg dx1 is this, dh du is this, dh dx1 is this. So if you do all the differentiation, you can stick it inside here. And then after that, if you stick this inside here, and then you stick ABC inside here, you can rewrite it into a transfer function. Then you can see it's quite standard. In control, we always like to write things like, you can see there's a S here. So we like to call this, you like to call this KP over TS plus what? You see, this thing here is your T. This thing here is your gain, KP. All right, then we like, oh, there's a square here. Okay, then we like to call this gain. Then sometimes we like to call this T the time constant. No. That's our usual way of doing things. So you basically look like that. But obviously, here you can see straight away KP. At different level, your K gain changes. It's very obvious. Then at different level, x2, the math says that your T also changes. So which means your transfer function, time constant and gain changes when the level of x2 changes. When x2 is here, you have a different transfer function. When x2 is here, you have a different transfer function. So your controller must change. If your controller don't change, the plant change, your controller change, you are not adapting, and then you will not get good control performance. So now I just finished the whole thing, another 10 minutes to show once you have the plant transfer function, then you can use any standard linear control design to design a controller for this plant. So I just give you an example of how to control a PID controller. So now the plant is given like that. You see, it's the same as this. Here is a square. I just make it a bit more general. If the plant, the T1 is equal to T2, then you will get this. All right, let's say the time constants are equal, T1 equals to T2, then you get this. If T1 is not equal to T2, then you don't get this, but it doesn't matter. So we just assume that a more general plant that include this one. So the plant look like that. Then the PID controller is written like that. I can't teach PID anymore. You just accept that the transfer function of the PID is, and to design the PID, you really means that you need to find the number of KC, TI, and TD. It's KC 1.2, TI 4.6, TD 7.2, or what. So you can use any valid design, control design method. So one of the standard method is to use pole placement. So I just use pole placement. That's one of the most common one. How does pole placement works? In just a 1 minute revision, if you have the plant here, sorry, if the controller here, the plant here, then this is the standard control loop, RY, then Y over R is GC/GP 1 plus GC/GP. And then pole placement means we look at the pole and make sure the pole is placed at a desired location. So this equation, now if you stick all this thing into GC/GP, you will get this here. Then this one, you compare to the standard closed loop characteristic equation. Now, why we always like to write in terms of omega and zeta? Because in control engineering, we have this kind of performance. I just write down here, maximum overshoot. We have this equation, this formula, which is given as minus pi zeta over all right, then settling time. So now if you say, I want my step response overshoot to be 10%, then you put 0.1 here, then you can calculate what is zeta. That's standard control engineering. So you get the value of zeta, you put it here. Then after that, you say, settling time, 5 minutes. So you put 5 minutes here. You already got the value of zeta. Then you get the value of omega. Then you put it here. So zeta, omega already settled. So this second order system settled. You see that's the third order. So that's why you need this here. But in control engineering design, there's such a thing called dominant pole theory. If you find the real part of this, choose alpha such that this is much more further to the left compared to the real part of this. So if this is a complex root, and then if the real part is -2, then choose alpha such that the real part is -20. So it's 10 times to the left of this. Then this one, even though it's there in the maths, but it will not affect your settling time and your maximum overshoot. In fact, it don't need to be 10 times, 5 times, 4 times already good enough. So which means if the real part of this is -3, you choose the real part of this to be -12. You basically doesn't really affect this much. So you choose alpha such that this is 5 times to the left or more negative than this. So once you have specified your overshoot, let's say 0.1, 10% is 0.1, so you stick it in. This is maybe 5 minutes, so you stick it in, you got zeta, omega, got this, you got this, you got this, you choose alpha, then this one will have the numbers. And then if you expand this thing, I will expand this thing here. If you expand this thing, you will have s cubed plus s squared all right, then you make sure that this is this. So to make sure, very simple, you just make sure s cubed and s cubed is the same, so they are the same. Then you make sure that you equate this to this. Then you equate, you equate this to this. Then you equate this to this, because s must be the same as s, so you equate this to. Then constant, you must make sure they are the same. So you have 3 equations. So you write down your 3 equations here, and then you just make your PID control parameters the subject. Then this will be a formula. Okay, then with this PID, you will get your specified performance of, let's just now I say what, 10% overshoot, 5 minute settling time. Okay, I will stop here tonight. So next week we'll go on to a new topic. And remember, next week, don't come here